Okay, let us start asking if you have doubts on what we have done last time, because we will now continue with the same reasoning. So we have discussed spin and Stern-Gerlach experiments. Let me summarize some of the things that we have discussed. We said that there must be some other Hilbert space, okay, together with the usual Hilbert space regarding orbits. And this Hilbert space, which has to do with the spin, is generated by two states, this and that. So the two plus 1/2 and minus 1/2 projections, eigenstate of SZ, okay? We said that there is this new object, which is the S, Sx, Sy, and SZ is a spin 1/2, okay? Therefore, S square, for instance, okay, is just 1/2 plus 1 on those states. There are two two states with this same S square, and these are the two states. Then you can form any possible combination of these objects. And we discussed a few things. For instance, there are eigenstates of, in fact, Sx that you can construct with those states. For instance, the state with plus 1/2, this time for Sx, we showed was 1 over square root 2 plus 1/2 plus minus 1/2, okay? And the state with the minus is just plus 1/2 minus 1/2. And we discussed the classical paradox that you have with this relationship. So we said if we select, for instance, from a first Stern-Gerlach experiment along Z, a pure state like, for instance, this one, okay, or the other, since this is really a mixture of these two, when we measure X after Z, we will find half and half probability of getting the electron deflected this way or that way, along plus X or minus X, and not 0, as you would expect, okay? So a spin along Z is really decomposed into two possible spins along X, and so forth. For Y, you have a similar expression, except that here there is, sorry, this is X, except that here there is an I, okay? Once again, the same paradox applies. So, okay. Now, these are kind of a particular case of a more general situation in which you can imagine, for instance, to take a Stern-Gerlach apparatus, aligning, however, the magnet, okay, so our Z direction, so to speak, in a new direction, which is a certain n, okay, in spin space. So n is just given by a certain angle theta, and as usual, by a certain azimuthal angle phi, okay? So you can always rotate the magnet of this Stern-Gerlach and put the magnetic field in this direction, or the magnetic field gradient, really. And then you will have, as usual, two spots, 50-50. You can block one of the spots and make a hole in the other, and therefore create now something like, for instance, this state. Now, what it is? This must be an eigenstate of the spin in the direction n. But the spin in the direction n is n dot s, okay? Now let's see. N is a vector. N is just the third component is cos theta. The first component is sine theta cos phi. The other is sine theta sine phi. And cos theta is the third component of n. Okay? The usual representation in spherical coordinates. Okay? So this operator here is equal to, well, if I write the matrix representation, I know that this is 1/2 the Pauli matrices. Okay? So this is 1/2 nx, the Pauli matrix as x, plus ny, the Pauli matrix as y, plus nz, the Pauli matrix as z, sigma z. Okay? So what is this? This is 1/2. Let's see. Sigma x, I know, it's 1, 1 in the diagonal. Okay? So this gives me nx, nx. Okay? Sigma y is minus I here and plus I here. So it's minus I ny plus I ny. And sigma z is 1 minus 1. So nz minus nz. Right? So this matrix, I can put these expressions there, is 1/2 cos theta minus cos theta. Here I have sine theta, which is in both. And then I have cos phi minus I sine phi, so e to the minus I phi. And here I have just sine theta e to the I phi. Okay? Is this clear to everybody? So this is the spin operator matrix in the direction n. So for the particular case where theta is equal to 0, for instance, then you have only this piece, 1 and minus 1 and 0 there. Again, sigma x, sigma z, sorry. If theta is equal to pi over 2 and phi is equal to 0, you will notice you will have just the sigma x. And if theta is equal to pi over 2 and phi is equal to pi over 2, you will have sigma y. For any other theta and phi, you have a more general combination. Okay? Now, in principle, this state, okay, is the combination of these two, which is eigenstate of this matrix with eigenvalue plus 1/2. Okay? So in order to find it, I should find what is the combination. So you know that I write any spin state as alpha plus the plus 1/2 plus alpha minus the minus 1/2, or in the vector notation it's just alpha plus alpha minus, and in the same notation the operators become just 2 by 2 matrices like this. So I must find two numbers such that this is equal to 1/2 alpha plus alpha minus. Okay? So this is the vector representing the state. Now, rather than solving this, it's a 2 by 2 problem, so one can find the eigenvalues will be plus or minus 1/2 and the eigenvectors. I give you the solution. Okay, this state is given by cos theta over 2, the state. Okay, let me make, when I write plus without anything, okay, it means the plus 1/2 z. And similarly, this is minus without anything. Okay? If I want to talk about some other state in some other direction, I explicitly put the direction index somewhere. Okay? So to make this short, this is cos theta over 2 plus the sine theta over 2 e to the I phi minus. Okay? In other words, the vector that I should put there is cos theta over 2 sine theta over 2 e to the I phi. Okay? Now, it is a bit strange because you see here there are cos theta and sine theta, and here I have theta over 2. But this is indeed this is indeed the solution. After all, remember that cos theta is really cos of 2 times theta over 2. So you can write as cos square theta half minus sine square theta half. And similarly, the sine theta, you can write it as sine of 2 times theta over 2. And this is just 2 sine theta over 2 cosine of theta over 2. And with these two expressions, it's very simple to show that this is indeed an eigenvector of this matrix with eigenvalue plus 1/2. If you want the one with the minus, okay, so this is this state, the state minus 1/2 z, n, sorry, it is associated to a very similar vector, but is sine theta over 2 and minus cosine theta over 2 e to the I phi. Okay? So these are the two eigenstates of spin in a given direction n. Notice that you find, again, the usual results that you already know. For instance, let us assume that theta is equal to 0. Then you have, obviously, 1, 0, and 0. You have 0 minus 1, but this is just the same. Okay? So let me just write this as minus like this. Okay? So apart from a sign in front, this is just 0, 1. Okay? If I have theta equal to pi over 2 and phi equal to 0, then you see here I have cos of pi over 4, which is 1 over root 2. And here I have sine of pi over 4, which is 1 over root 2. And which is this. And the other is 1 over root 2 and minus 1 over root 2, which is this. Okay? And similar, if you have theta equal to pi over 2 and phi equal to pi over 2, this gives you an I. Okay? So you have the eigenvector along y, which have the I here. Okay? So you see that this is a generalization of these formulas here for an arbitrary direction, theta and phi. And what is nice about this is that now you can play the following conceptual experiment, which can be done in practice. You first prepare, so the usual beam of silver atoms, okay, which passes now through a Stern-Gerlach apparatus, polarized along n. Okay, let me indicate as SGN. Okay, it means in the direction n. Then you have the usual screen, and for instance, you block one and you make a hole, and therefore here you have this state. Okay, so all the atoms passing by the hole are states of plus 1/2 n. So if you measure again with a similar apparatus, you will find 100% of them and 0 in the other spot. However, you can make now a second experiment with the Stern-Gerlach along z. Okay? In other words, you can measure z after having measured n and projected on a certain plus 1/2 n. What you will find? So what percentage would go here and what percentage would go there? So what is the probability, in other words, of finding minus 1/2 z and the probability of finding plus 1/2 z if you have this state selected by the first experiment? Right. So the probability of obtaining this is the square of this. Okay? So it is equal to cos square theta over 2. Okay? So this is, let me write it here. The probability of finding plus 1/2 z in the state plus 1/2 n. Okay? So it is equal to the modulus square of this. Okay, you make a projection of the state with the state along z, and you take the modulus square. The projection just gives you cos theta over 2, you square, and this is equal to cos square over 2. If you calculate the other, so this one, you have a minus here, a minus here. You have to take the other piece, take the modulus square, you get sine square theta over 2. Okay? So I like the case, for instance, when theta is equal to pi over 2. Remember, we said if we measure x, we will find 50 and 50. Yes, because you have 1 over 2 and 1 over 2 here. If I measure in another direction, the two will be unbalanced. So I can actually verify that this is different from that. Okay? So in any direction theta, I should find a probability of getting one spot definitely different from the other, in principle. Okay? So I can verify this. Obviously, I can calculate the average as well. So what is the average value of Sz that I would measure on a state, for instance, like this? Well, the average is very simple. The average value of Sz, I know that is equal to, well, I can calculate it from the very definition, or I can just use these two results already. So the average of Sz on a state plus 1/2 n is nothing but, if I get this, I get 1/2, but I get 1/2 with the probability cos square theta over 2. I get minus 1/2 with the probability sine square theta over 2, and the result is 1/2 cos square minus sine square of theta over 2. You read it there, it is 1/2 cos theta. Okay? So the average I get is 1/2 cos theta. All right? Now, you can repeat the same type of exercises. And for instance, ask yourself, what is the probability of measuring now x in a certain direction on a state prepared like this? Okay? So what I should do is exactly a similar calculation. Let me just hint to the calculation. So you want the probability of measuring plus 1/2 x on the state plus 1/2 n. Then this is equal to the projection of the state plus 1/2 n on the state plus 1/2 x, and then modulus square. Okay? So I should take the scalar product of this object, not with this or that, but with this, for instance, or that. Okay? So there are more terms, and you can calculate it. Similarly, you can calculate the one with the minus. Okay? So the scalar product with this, for instance. It's very simple, not particularly complicated. And similarly, you can calculate the average of Sx now on the state plus 1/2 n. The way to do it, again, either you use these results for the probability, and you sum 1/2 a certain probability minus 1/2 the other, or you just calculate directly. You know how this matrix is made, okay? It's a matrix 1/2, 0, 1, 1, 0. You know what this state is. It's a vector, for instance, cos theta over 2 sine theta over 2 e to the I phi, okay? And on this side, you should put the bra, so cos theta over 2 and sine theta over 2 e to the minus I phi, okay? You do this small scalar product, and you will obtain a quite simple result. You will obtain 1/2 sine theta cos phi. Okay? believe me, I mean, it's a simple calculation. And it requires also using a little bit of those formulas. The surprising result is that while individual probabilities are non-trivial, the average is more understandable. You see, the average value of SZ is just 1/2 cos theta. After all, n has a z component which is just cos theta, okay? So you understand that the average of SZ is just this. The average of SX is just this. And, well, you're not surprised perhaps now if I tell you that the average of SY is just this, okay? In other words, I can just write here, if I have any component of the spin, and I measure the expectation value on a spin state plus 1/2 n, what I find is the pretty understandable result that this expectation is just 1/2 the vector n, okay? So the average of the spin vector operator on a state directed along n is just n. But each individual result is obtained with probabilities that are highly non-trivial. In particular, if you have even a state along z, you can measure with half and half probability, for instance, a spin along x and so forth. All right? So hopefully this gives you an idea of, I mean, how delicate it is to deal with spin. I mean, it's very simple indeed. I mean, it's 2x2 algebra, but you have to be a little bit careful. Some results are easy to understand. Other, well, are classically counterintuitive. Okay? Very good. Now, okay. Let me just do now with you an exercise which uses a little bit of this. So for instance, what should I erase here? I am uncertain. Let me just leave these two expressions. We eliminate some of this. Do you have questions until now? Are you following? Yes? Okay. Okay. Do I need this? No. So suppose that I put a certain system in a magnetic field. Now, you know that the Hamiltonian, for instance, suppose that it was an hydrogen atom. The Hamiltonian of the hydrogen atom is already modified by the presence of the magnetic field by this term. Okay? We have discussed it yesterday. And you know that this gives rise essentially to a term mu b L dot b plus a b squared term. Okay? So already at the orbital level, the magnetic field enters in some sense. However, if I'm, for instance, looking at an hydrogen atom in the ground state, L is really 0. So at that level, there's not much effect due to this term. There would be an effect due to b squared, okay? But let me forget about this thing, okay? This is not the center of my attention now. However, if I put a magnetic field on this system along, for instance, Z, I know that there is another term that is this. Okay? The field is along Z. So I have just SZ term, okay? So this term is the analog of this, now specialized to just a field in the Z direction. And I know that this is there because it comes from the non-relativistic limit of the Dirac equation. Now, how do I study this Hamiltonian in the presence of the field now. So let us return back to our description of hydrogen. So forget about this term. Suppose that hydrogen was the usual hydrogen in the in the zero magnetic field, so something like p squared over 2m minus e squared over r. Now, let us look back at the spectrum. You remember that we had essentially zero of energy here. This is energies. Then I had a state which we called 1s, at an energy which was minus 1 Rydberg. All right? Now we know that this state has an orbital wave function that was just psi with n equal 1, L equals 0, and m equals 0. But we know that this is not all. We know that there is also a spin wave function, which we completely ignored at the time when we studied this problem. And this object, for instance, could be plus 1/2 or minus 1/2, say, along the z direction, for instance. Okay? So really, rather than having one state, I have really two states. The electron can be in either one of the two. In other words, can stay with a spin up or a spin down. The energy would be absolutely the same. Okay? So there is no way of telling where the electron is, in which of these two states, until I turn on a magnetic field. We'll see now the effect. So in absence of magnetic field, so here I have the magnetic field, for instance. Okay? In zero magnetic field, these two states are totally degenerate. They would coincide. How should I draw? Like this. Okay? Totally same energy. The same argument applies to any other level. For instance, the 2s level, okay? It's really two levels, okay? A spin up and a spin down. And also the 2p, okay? They are really 3 times 2. Forget about this being, because I need some space, so this is not b now. This is really 6 states, the 2p. So the 2p with the up spin, sometimes rather than writing plus 1/2 z, I write just up, the arrow, okay? Or the 2p with the down spin, okay? They are totally degenerate. And so on in the rest of the spectrum. Now you see immediately that when I turn on a magnetic field, for instance, this state, the up spin and the down spin states are no longer completely degenerate. One is pushed, for instance, the up spin is pushed up by a certain amount, which is 2 mu b times 1/2 times b, okay, so by an amount mu b bz, okay, and the other one is pushed down by an amount equal in the opposite direction, so minus mu b bz. So remember, this quantity, mu b bz, which you see enters in the splitting, is a very small amount. For a field of 1 Tesla, we discussed, this is 5.8 milli-electron volt. Okay? So this is 5.8 milli-electron volt at 1 Tesla. So you can realize for a lab field, which is much smaller than this is a very, very teeny number. Compared to this number that is of the order of 10 electron volt. So you get some small splitting in the field. All right. The same thing happens everywhere. Now we are going to see if there is any relevance of these very small splittings. It looks like they are so small that maybe they are not important. And I will show you that this is not the case. So suppose so. Okay. So let us summarize this discussion by saying that the energy En now will be also attached to them another label, the plus or minus, the spin, okay, plus or minus 1/2. And as a function of the magnetic field, Bz, this will be just the En that you calculated in zero field plus or minus mu b b. In other words, there is a splitting that is linear in the field, and this splitting is called Zeeman splitting. Okay? So the field splits due to the spin the energy levels. Okay. Suppose that I prepare now my system in a certain state, for instance, in this spin state. How do I do that? For instance, by going through a Stern-Gerlach apparatus. Okay? So after exiting the Stern-Gerlach apparatus, I know that the wave function of my system would be, so at psi at some t equals 0, the exit time from the apparatus would be psi n, some, I don't care which level, okay? This is not important. This is not what we are going to study, times 1/2 direction n. Sorry, there is an ambiguity. I shouldn't probably use n here. This is some, some eigenstate here. Any other letter? Okay, let me put just n with the underline. Hopefully this doesn't confuse you. Okay, so it's some excited state of the atom. Any other letter you like? K, alpha, whatever, K. Okay. This is some energy here, okay? And I know that is split now by this object when I turn on the field, like this. Okay. Now, the state that I have out of the apparatus is this, okay? As you see, this will play essentially no role. And this is plus 1/2 n. Now, I subject this object, okay, so from t equals 0 on, to a uniform magnetic field in the z direction, okay? So I have this atom here, which is prepared in a certain spin state, plus 1/2 n, and is now in a field which is bz in the z direction. So I ask you, what is going to happen to the wave function, okay? Well, the thing is pretty simple. What I have to do is to apply the evolution operator. So psi at time t will be e to the minus I, the Hamiltonian, over h bar, times psi at time t equals 0. The field is constant, okay, in time, okay? So what I have here is e to the minus I h0 plus 2 mu b sz bz t over h bar, acting on the state orbital part, this is the orbital part, times the spin state, plus 1/2 n. Now, first of all, I should probably tell you a little bit of more. What does it mean to sum a spin operator to some operator like p squared over 2m? I mean, they act in different Hilbert space. What does it mean to sum them? Well, there is an implicit assumption that I never really make it explicit, is that if I have, for instance, h0, okay, when acting on a certain state, for instance, a state of the type orbital times spin, then h0 really acts only on this, and it acts as an identity in the second piece, okay? So it does nothing on the spin, and it acts just on the first one. So mathematicians tend to write these things with the unit operator and the cross to really make explicit the fact that H acts only on the orbital Hilbert part and not on the spin Hilbert part, okay? I tend to omit this. In a similar spirit, when I say the spin, for instance, spin Z, acting on, for instance, on a state like this, it means unitary unit for the orbital part times spin for the spin part, okay? So hopefully this is clear to you. Okay? So the spin doesn't care about the orbit, and vice versa. The Hamiltonian, the usual term, okay, that we have studied so far, doesn't care about the spin. In the same spirit, the H0 and SZ really commute. They don't talk to each other. They work on different spaces. So I can really split this exponential in two pieces. One, which involves this, which acts on the orbital Hilbert space, and this other piece that acts on the spin Hilbert space only, okay? So they work on different things, and they don't care about each other, okay? This is just to tell you that what I'm really looking at here is, let me just write it this in a simplified way. So this orbital part really proceeds with its own Hamiltonian, and the spin part, which is this, also proceeds with its own term, that is 2 mu b sz bz t over h bar, acting on plus 1/2 n. Okay? Yeah. The part there? Okay. I explained to you last time that the Hilbert space is really a product of two pieces. And I make this almost explicit. When I write a state, you see it's an orbital wave function times a spin wave function that, I mean, these two objects really live in two different spaces, okay? So it's not the product of the usual sense in which you multiply two functions. It's really two things living in the different spaces. Now, if I act with an operator which involves only the first space, I really act only on this, okay? So that operator has the effect of being just the unit operator in the other, okay? So an operator like H0 really means H0 times the unit in the spin part. In other words, it does nothing to that, and it does everything to that, okay? In a similar spirit, when I write this is, you see, only spin, which I should write more precisely as unit for the orbit times spin acting on the spin, okay? So really, this does nothing on that, and it does everything to that, okay? So that's always the spirit. When I have an operator, I should decide if this works on the orbit or on the spin. In a while, we will encounter a strange example of an operator that indeed does both. It's an operator, which we'll find in a short while, that is called the spin orbit, okay? So this has two legs, okay? It's really a piece acting on this and a piece acting on that, okay? And we will see that some combinations have to be taken in order to work with this, okay? But for the time being, I'm always considering operators that either regard the orbit or regard the spin, and they are therefore accompanied by a unit in the other leg, all right? So that's all I wanted to say there. Now, so just to make the thing short, you see that the evolution of the orbital part is not what I'm really interested in. This, if this is an eigenstate, this will be some overall phase in front of the state. What I care more is this part, okay? So let me write again here the Where should I write it? Maybe here. Let me write the two states here. Cos theta over 2 sine theta over 2 e to the I phi. This is the state plus 1/2 n and minus, sorry, let's put the plus here. So sine theta over 2 minus cosine theta over 2 e to the I phi to be the minus 1/2 n. Okay, so I have now some space. Okay, so what I'm saying is that the state at times t is some orbital state at times t times, I now tend to be more mathematicians, and I put this product there. Most of the times I omit it, okay? So the orbital part does something which is perhaps just a phase, times, let's see what this is. Now, Sz is just, when acting on a certain state, is just essentially, well, let's see. This is e to the minus I 2 mu b bz t over h bar. These are all constant. Then I have what? I have Sz, and then I have this state that is equal to, let's see, there. It is equal to cos theta over 2 times the state plus sine theta over 2 times e to the I phi and the state minus. Okay? Now, this and this are eigenstate of Sz. Therefore, it's simple to calculate the effect of this exponential of Sz on this or on that. Okay? Since this is an eigenvector of that, the effect will be just cos theta over 2, the same state, times a phase. How much is the phase? The phase is e to the minus I 2 mu b b t over h bar, and this will be 1 over 2, right? Because this is the state with, say, plus 1/2. Let's put it explicitly. Okay, so I put here a 1 over 2. All right, so the 2 and the 2 goes. And you see that you have essentially this energy, mu bb, times t divided by h bar in front of this. What about this? I have similar thing, sine theta, e to the I, the phase. The phase is due to the direction of the. So I write this thing certain times like this, certain times like that. Is the same. Okay? Okay. And then I have this operator that now has eigenvalue minus 1/2 on that. Okay? So it gives you a phase that is exactly the opposite of this. All right? So it is e to the plus I mu bb t over h bar. Okay? Is this clear? So in the first piece, this thing gives me a phase with the minus. In the second, gives me a phase with the plus. Now, so if I put this overall phase just in front of everything, I will find that the state is the orbital part at time t times a phase e to the I mu bb t over h bar times, let me put it here, the cos theta over 2 times the plus 1/2 plus the sine theta over 2 times e to the I phi times, well, if I put the minus in front, I have plus 2i, okay? Let me just write it, e to the plus 2i mu b b t over h bar, okay? So I put e to the minus in front, which means that this becomes e to the plus 2 in such a way that I have only, the correct thing. Okay? Now, I forgot the state. Minus 1/2 n. Okay. Now, suppose I now, after a certain time t, where the system is staying in this magnetic field for a certain time t, and now I measure again the spin. Okay? So I do measurements. What is the average value of the spin that I will obtain? You see immediately that the new spin state is pretty similar to the previous one, except for this extra phase here appearing close to that. You see, I could write really this object. Let's write it again. So this state is really cos theta over 2 plus 1/2 n plus sine theta over 2 e to the I, the phase, the original one, which was due to the direction I chose, plus 2. Well, this is what? This is this energy. So if you want 2 mu b, where is it? Here. 2 mu b b is really the splitting of energy induced by the field. So the delta E due to the field times T divided by h bar. Times minus 1/2 n. So if you were to tell me where the spin is pointing now, probably the answer comes automatically. It's like if phi is increasing with time. Okay? Notice phi is this angle. Theta is fixed. Theta is there, fixed. But the angle phi is really increasing with time with a certain frequency, okay, omega. It is called Larmor frequency, okay, and it is precessing like that. You see? The phase phi is increasing steadily with time with that frequency. Now, this is just spin precession that we have described. So if I prepare a certain spin state in a certain direction and I put a magnetic field along z, like a top would do, okay, the top precesses around the gravity field. Okay? Now, this precession occurs with the frequency omega L, which is 2 mu b b divided by h bar. If I put the value for mu b, remember, is e h bar over 2 mc. Then I put the factor 2. Then I put the b, and then I divide by h bar. You see that h bar disappears completely, and also the 2, and I get eb over mc. Okay? So this frequency here is indeed very classical in spirit. Okay? If I have a particle in a certain magnetic field, a particle of charge E and mass m, it rotates in the magnetic field with this frequency. Okay? That is the Larmor frequency, or the cyclotron frequency, as it's called in many ways. Okay? So the frequency with which the spin rotates is exactly the same that the charge would do in a magnetic field. Now, is this clear? Okay? Yeah. Yes, I'm sorry. I just changed all of the sudden. No, otherwise it would be a mess. Okay? So the state originally was n. I wrote n in terms of z states. It's 2 of them. each one acquires a certain phase. I put an overall phase in front, and I see that essentially the second piece has a phi that is increasing. It's increasing linearly with time with a certain frequency, which is this object here. Okay? This means that if I do some measurements at time t of the value of the spin, okay, I would find expectation value perfectly compatible with the spin that is now precessing. Is this clear? Okay. Yeah. Yes. Okay. Is it clear that the state at time t is this? Okay? This is the state at time t. Okay. Now let me calculate with that state where I need some space. Let me just do it here. So the state at time t is essentially an orbital part at time t times a certain phase here, e to the minus I mu b b t over h bar, times cos theta over 2 plus 1/2 plus sine theta over 2 e to the I phi plus omega L t times minus 1/2. Now, let me ask the following question. What would be the average value of the spin I would measure on this new state? Okay? Experimentally, I should repeat several measurements at a given time t. If I am a theorist, I'm just calculating the expectation value of the spin operator on the new state at time t. Now you see the spin doesn't look at the orbit, okay? Therefore, this part is totally irrelevant, whatever it is. This phase also is not relevant because it cancels between here and there. So all I have to do is to calculate the expectation value of the spin on the following spin state. Okay? But we said pretty in general that the spin operator, if you calculate the average, for instance, along a certain n, what you will find is just 1/2 n. Okay? Now what you have is exactly a certain n where, however, n depends on t. And it depends on t just because the phase phi has changed. Okay? So the phase at a certain time t is equal to phi plus omega L t. Okay? So it's like if this n is rotating around z. Is this clear? It starts at time z from the place where you prepared, and it rotates as time advances in this way. Okay? So this is n of t for me. Same theta, but a phi that is changing with time in this way. All right? So if I calculate this thing, I get 1/2 n of t. Is this clear now? Spin precesses, and the average value is changing. Okay? So for instance, the average value of z is constant, you see, because the theta is not changing. So if I keep measuring sz, I will find always the same number, cos theta over 2 on average. When I measure, I always find plus 1/2 or minus 1/2, but with probability that are functions of theta, and the average is cos theta over 2. But if I measure x, for instance, well, this value is going to change, even the average. Okay? For instance, when I'm here, I have a certain average which is positive. I wait half a period of the full rotation, and I will get opposite result. Okay? I wait a quarter of a period, and I get 0 on average, and so forth. All right? Is this clear? Now, this little toy, okay, this fact that the energy levels in presence of a magnetic field are split, okay? They become split by a certain energy, delta E, which is essentially 2 mu BB, is not only responsible for instance, spin precession. If the spin is not aligned along Z, then it will rotate around Z. It's also responsible for more kind of very important properties. For instance, if you prepare your system, and your system is, for instance, here in the ground state, so with the spin down, and then you send a microwave type of frequency, because these are very, very small energies, okay? So you send a very small electromagnetic field, which has, for instance, a component along X. So something that is proportional to Sx, but with some cosine of omega t, where omega matches exactly this energy difference. This is what people do in nuclear magnetic resonance. There is a field Z that aligns the spins, and then they send a transverse field that oscillates. Whenever the frequency matches exactly a splitting of levels, then that frequency is absorbed. We will describe this later on when we do perturbation theory. Why is that if you send a time-varying field with the frequency that matches the splitting, the system flips the spin and absorbs energy? It is a bit what you very well known atoms do when they absorb photons, okay? The photons match exactly the energy splittings, and the photons are an oscillatory perturbation, and they promote the excitation of the atom from one state to the other. Well, this is nothing but the same mechanism, but you can tune now the frequency of your field and see where it is absorbed. By seeing where it is absorbed, you have a very precise measurement of this splitting, okay? And with that, and with a lot of ingenuity, you can actually map things and visualize even things, okay? That's a really wonderful thing. I mean, now in the hospitals, they can really look at very careful places, in very, very thin, and they can really have wonderful information on whatever part of your body you want, okay? The mechanism behind is just this, okay? So it's a resonance phenomenon that you have because of this splitting of energy in the field. Okay, so I think that this is enough for this story, unless you have questions. But I would like to finish essentially the same thing with a small little note, which is the following. And yeah, of this. What do you exactly want to know? Why the spin rotates? You want to know this? I mean, what this is telling you is that the average value of the spin changes with time. But not all of them. The SZ doesn't change because you see n, this function here is just this, but with the phi that depends on time. Okay, and the phi depends on time in this way. So this is just telling you that the average value of the spin, which you prepared in a certain direction at time t equals 0, due to the presence of the field in the z direction, changes. So if you make measurements at a later time, you will find probability values that sum up in the end to averages that are changing in time. Is this clear enough, or? No. Let us think now. If there is still a doubt, let us clarify it now. Is it clear that this is a spin state? Okay, first of all, and that this spin state is, for instance, depending on time. Is this clear? Now, the spin state is depending on time. So in principle, you would imagine that the average should depend on time, okay? If the state depends on time, the average value will, in general, depend on time. Okay. Suppose that you have a top, okay? The top rotates, okay? And you know that this means that there is an angular momentum, okay? Now, in free space, the angular momentum is conserved, and the top would keep rotating, maintaining the direction. Now, I put this thing in the gravitational field. I know that the force acts on the on the angular momentum with a torque, exerts a torque. And the torque makes the angular momentum changes. Are you surprised of this? The angular momentum changes. That's what physics tells you, okay? Now, I do a different thing. I put the spin in a certain direction. In absence of anything, free space, the spin would be there forever, at all time, okay? So I keep doing measurements, and I always find the same expectation. Now I put the magnetic field, which plays the role of the gravitational field, and this exerts a torque. And it makes the spin rotate, exactly like the top rotates. This is it, okay? Mathematically, it's given by this thing, which is indeed probably simpler than the top type of exercise, but this is exactly the same physics. Precession of an angular momentum around a certain force that provides a torque.
So in this case, it is the spin down that rotates because of the...
Well, I mean, remember, the spin is always a combination of up and down. It's not that rotate the down. I mean, the down is down, the up is up. Both of these they don't rotate. It's the mixture of them that changes a phase. I mean, it's something that it looks a ridiculous thing, because after all, the modulo square of this and the modulo square of this are still the same. It's just a phase that is changing, okay? So for instance, if I just want to know what is the probability of measuring plus 1/2, it's still cos square of theta over 2. What is the probability of measuring minus 1/2? Still sine square of theta over 2. This phase is irrelevant for that measurement. And this shows that, indeed, if you measure the spin along z, you always find these same probabilities, and therefore always the same average, which is cos theta over 2. So it's misleading to say that the spin down is rotating. I could put even the phase in front of this. I mean, after all, it's a relative phase, okay? So if I put this phase in front of here, I can still have the same expression, except that I have to put here e to the minus phi plus omega L t, okay? So I can put this out, then e to the minus here, and 1 here. Now, what does it mean? That the spin up is now rotating? No, it's just a relative phase. All it matters, when I write this spin in this way, you see, I could have written in different ways. The important thing is the relative phase. I mean, I could, for instance, put here e to the phi over 2, e to the minus I phi over 2. Indeed, in certain books, you find different phases, okay? So don't be just misled by the actual fact that the phase, I put it there. That's not important. it's the relative thing that matters, okay? And the relative phase is changing between these two states. And this is important, okay? Yeah.
And what would be the value if we take average on time? Okay, over a period.
Well, then obviously the x and y just average to 0 and only z remains, okay? Yeah. But the people who do NMR can control time very well. I mean, they have they can really wait for half, a quarter. I mean, they do wonderful things. So I mean, time and frequencies are very well measurable. So they are precise measurements that you can make. And this could be relatively long time, because after all, we're talking about relatively small frequencies, okay? These energy splittings are not gigantic, so I think that the measurements can be pretty accurate. Yep.
Could you tell us an overview about the factor 2?
This factor 2 here? Oh, no. No. I prefer not. I mean, this really comes there from Dirac. Okay, so unless I do a derivation, which I'm not ready to do, I would never be able to explain why there is a 2, rather than 1. I mean, the analog for L would have just plus L times mu b. Unfortunately, I mean, it's hard to really justify in any reasonable way that is not just doing the derivation this factor 2. Okay, so let me just finish this lecture with a final small topic that indeed is very strongly related to what we have done. Until now, if I ask you what is the average value of the spin on a certain state that is evolving in time, you just do this. You just calculate this. But this is what? Psi of t is the state, so it's e to the minus I h t over h bar times the state at time 0. Okay? So I can really put this thing there and say that this is equal to, now if I use the bra here, I would have psi of 0 e to the I h t over h bar. And then I have still the same spin operator. And then I have here e to the minus I h t over h bar, psi 0. Okay, so in this new way of writing, you see all the time dependence is there. The state is fixed, is the state at time 0. So in some sense, I can adopt the two possible views. One is that the state evolves in time, and the operator that I want to measure, say, is fixed. And this is called the Schrödinger picture. Or I can adopt another strategy in which I say the state is really fixed. And what it changes is the operator that I want to measure. Okay? And this is called the Eisenberg picture. And I call this object the Eisenberg operator S at time t. Okay? So it's nothing but where I put the evolution operator. If I put it in front of the state and I think the state is moving, or I put it close to the operator, and I say the operator is changing. Okay? It's just the same, very same thing, just seen in two different ways. Okay? This is called the Heisenberg picture. Now, the operator at time t now, you see, has these two unitary operators. I can actually calculate an equation for it. So follow me for a very short derivation. So let me calculate what is what is I h bar, the derivative of this spin operator. Now, this is just the derivative of this object or the derivative of that object. Okay? Now, this is I h bar coming from here. If I take a derivative of this, I get what? I get I h down in front, then I get over h bar, and then I get the same thing, s e to the minus I h t over h bar. This is one term. Then I get another term, which is, again, I h bar, then e to the I h t over h bar. Now I don't touch this, I touch this, okay? So s is there, and then I take here minus I h over h bar e to the minus I h t over h bar, okay? Now, two derivatives, because there are two exponentials there. You have to be careful with the order, however, okay? So you see, when I take the derivative of the first piece, I can put the h there or there, but not past the s, okay? This is always before the s. And similarly here, I can take the h here or there, but not before the s, because the order is important. So h commutes with this exponential, but not with s. Okay. Now, you can collect a few things. For instance, you see that h bar really goes. And also, I and I is a minus, okay? So you see immediately that this is equal to minus h times the same operator, so sh of t. And this is what? Let's see, this is I, and I is a minus 1, so it's a plus. The operator, I can bring this to the right of its exponential because they commute. So I see again the spin operator, Eisenberg, times h. Okay? So what is this? This is equal to the commutator of sh of t with the Hamiltonian. Okay? So you see that the derivative of the operator in Eisenberg representation is just the commutator of the operator with the Hamiltonian. Is this clear?
Yeah, but h bar dy dt is the operator for the Hamiltonian, right?
Right.
So,
No. I understand what. Okay, there is a tendency. Oops, I'm sorry. The Schrödinger equation is this. And by the way, it's true even if h depends on t. So there is a tendency of saying that this is equal to h, which is almost true. But this, I mean, in some sense, this is an operator. This is just a derivative with respect to time. Time is a parameter in our quantum mechanics. It's not an operator, okay? We have to be a little bit careful. While x and p are operators and are conjugate to each other, time and energy are a bit conjugate, but not on the same level, I mean, at least formally, than x and p. You do not consider this to be an operator. This is just a derivative with respect to time, while the Hamiltonian is an operator, okay? So you should never be so fast and say, okay, this is just Hamiltonian. Otherwise, I would derive a very strange equation. Hamiltonian times s equal to, for instance, minus the Hamiltonian s plus, looks like I can simplify things or get strange equations with, okay? Like twice the Hamiltonian times s equal to s times that. No, these are all wrong, okay? So don't be too fast on this identification and just use it as a reminder for the Schrödinger equation, which is indeed behind everything we have done. I mean, this is behind the fact that the evolution operator obeys a very identical equation, essentially, okay? And, but by the way, some of what in fact, all I've said can be generalized even when h depends on t, because the only thing that I use is really this, that holds also if h depends on t, okay? The calculation I've done for you is explicitly with a time-independent Hamiltonian, but you can repeat with little adjustments the proof even when the Hamiltonian depends on time, okay? Now, yeah.
It seems like S doesn't depend on T. Spin.
I told you it's a different way of seeing things. Until half an hour ago, the spin operators were operators fixed in time. They're called Schrödinger picture operators, just operators fixed in time. And the states evolve with the time evolution operator. But now I changed picture. I changed the way of seeing the same thing. I mean, after all, my object is the average value of the spin operator, okay? I can regard the time evolution as acting on the operators, okay, rather than on the state. And now the operators depend on time. It's just a different way of looking at the same thing. It's not my fault, it's Heisenberg's fault, okay? He introduces this way of looking at things, okay? So don't tell me that the operators don't depend on time. Just tell him. Yeah. Sorry, okay. You see, you know more now than this. Okay, it's true. He is telling us that the derivation I have done applies if the operator inside here doesn't depend on time. If there is a time dependence of this, then I should add here an extra term. Correct, yes, but we will, not consider those cases. Yes, you can write a more general equation with the time dependence of that. Okay, sorry, I misunderstood your question. Okay, so this is the equation that I have derived in the case where h doesn't depend on t, but it applies also with small changes to the case where h depends on t, and for the case when the operator doesn't depend on time. Otherwise, I would have another piece that is plus I h bar, the explicit time derivative of the operator, essentially, okay? With the two evolution operators in front, okay? So with the e to the minus I h t over h bar and e to the minus I h t over h bar, okay? This extra piece I'm omitting because the operators I'm considering are just fixed in time. Now, let us look at this object here. This is, it's written really here. You see, it's S with the Hamiltonian just before and after. But H commutes with all these objects, okay? So I can also write the same thing as e to the I h t over h bar, the S commutator with H, e to the minus I h t over h bar. Okay? This would be probably a better way of writing this. In some sense, you're seeing now that what matters is the commutator of S and H. But now, let me see. Suppose that you have in the Hamiltonian H0 plus what we said before is 2 mu b b sz. Okay? So what I have here is the commutator of S with this Hamiltonian. And obviously S commutes with H0, because H0 I have assumed doesn't depend on the spin at all. And all I have is the commutator, so it's 2 mu b b, the commutator of S with Sz. Now you see immediately, if I consider Sz, for instance, here, now Sz commutes with itself, okay? So the result would be 0. So this immediately tells me that I, h bar, the derivative with respect to time of Sz Eisenberg representation should be 0. Okay? This immediately implies that Sz Eisenberg is not depending on time, which means that the expectation value, after all, this is just the expectation value of the spin on the state. Now, if the operator Eisenberg doesn't depend on time, it means that the expectation value is just constant in time. Okay? So this is telling you that the average value of Sz is constant in time. All right? And indeed, it tells you even more. It tells you that the expectation value of any operator that commutes with the Hamiltonian, suppose that instead of S I have any other operator, okay? This operator, if commutes with the Hamiltonian, then its expectation values should be constant in time. Okay? That's the reason why they're called constant of motion. Okay? Things that commutes with the Hamiltonian preserve their average values in time. All right? In particular, the Hamiltonian itself, if time-dependent, commutes with itself, and therefore the average energy is preserved, is conserved. Okay? Notice, that doesn't mean that this is necessarily one of the eigenvalues. It can be a complicated superposition of energy eigenstate, but the average is preserved. Okay? On the contrary, the spin along x and y do not commute with Sz. Okay? And therefore, their expectation value changes with time. And indeed, there is a very small, after all, remember that the algebra of commutator is pretty much, for angular momenta, is pretty much like the vector product. Okay, so you can verify that this is just like the vector product that enters in the torque. Nothing but that. So precession is just the vector product that that makes me rotate around the z direction. Okay? So I just wanted to finish with this remark because, you encounter from time to time this Heisenberg representation, and therefore it's good to know what it is. Okay? It is simply putting the time evolution in the operators. Indeed, there is a third representation that is called interaction representation. We will probably discuss a little bit when we do perturbation theory, which is kind of an interpolation between the two. It's doing a little bit of the Hamiltonian, putting it in the evolution of the state, and a little bit in the evolution of the operators. Okay? You usually split the Hamiltonian into two pieces, H0 plus an interaction, and you do half this and half that. So, okay? But this is not the center of certainly our discussion, and therefore I will just briefly mention later on. Okay, so next time we do spin orbit and relativistic effects, and we learn a very important subject, which is how to add angular momentum. Until now, we have the orbital angular momentum, we have the spin or angular momentum. They don't talk to each other. Therefore, you can just separately think of each one in a completely unrelated way. Next time, we will learn that Dirac and relativistic theory predicts that there should be a term like that in the Hamiltonian. Now, this term, as you see, it's pretty nasty in the sense that there are terms like Lz, Sz. They are fine. They don't change the z projection, okay? But there are terms like Lx and Sx and Ly and Sy, which, when acting on any eigenstate of Lz or Sz, they just change it, because these are, after all, combination of L plus, L minus, S plus, S minus, okay? So you take an eigenstate of a certain spin given and Lz given, and this scrambles it, okay? So there must be a way of learning how to really combine these two things in another object. And we will learn that the trick is pretty simple, and it is essentially the sum that matters. Because when you take the square of the sum, obviously I should think of this as L times the identity in spin space and identity in orbital space times S. This is the precise thing. In any case, when I sum the two and I square, I get L square plus S square plus 2L dot S. You see that this object really is like in the belly of the sum squared, okay? Because after all, these are objects that we know very well, L square and S square, and this new beast is nothing but related to this and to the sum square, okay? So we'll have to work with the operator sum of the two angular momentum, which is called total angular momentum, and we have to learn how to really classify its eigenstates in terms of eigenstates of, say, L square and LZ, S square and SZ, okay? So we will learn how to construct eigenstates of J square and JZ starting from just product states of L square, LZ, S square, SZ, okay? Once we learn how to do this, this beast will be simple. So this is the plan for next lecture.